going to revisit parabolas. This time we're going to look at how to write equations of parabolas in standard form and graph parabolas. Again, how are parabolas used in manufacturing? A mirror, or the reflective object in the shape of a parabola, has the property that parallel incoming rays are all reflected to the same point. Or, if the point is a source of rays, the rays become parallel when they are reflected. In Chapter 6, you learn that the graph of an equation in the form y equals ax squared plus bx plus c is a parabola. A parabola can also be obtained by slicing a double cone in a slant as shown below on the left. Any figure can be obtained by slicing a double cone is called a conic section. Other conic sections are also shown. A circle is made from a slice that is parallel to the bases. An ellipse, the slice is slightly not parallel, as opposed to a parabola, it's very not parallel. And a hyperbola, the slice is made so that it is perpendicular to the bases. A parabola can also be defined as a set of all points in a plane that are the same distance from a given point, called the focus, and a given line, called the directrix. The parabola to the right has a focus at 2, 3, and the equation of the directrix is y equals -1. You can use the distance formula to find an equation of this parabola. Let xy be any point on this parabola. The distance from this point to the focus must be the same as the distance to the directrix. The distance from a point to a line is measured along the perpendicular from the point to the line. So to find the distance from xy to 2, 3, and the distance from xy to x, -1, we're going to do the difference in the x's squared plus the difference in the y's squared, and again the difference in the x's, which is conveniently 0, and the difference in the y's squared. And you square both sides, voila, the square roots are gone. And then they want to FOIL out the y's, because then magically when we can subtract y squared from both sides, they're going to drop out, and add 6y to both sides, and then they subtracted the 1 over here. So the lovely thing about this equation is they've solved it for y, divide both sides by 8, or multiply by 1/8, so this would be something that we could type into the table feature of your calculator. An equation of the parabola with a focus at 2, 3, and a directrix y equals -1 is, we just found, y equals 1/8 x minus 2 squared plus 1. The equation of the axis of symmetry for this parabola is x equals 2. The axis of symmetry intersects the parabola at a point called the vertex. The vertex is the point where the graph turns. The vertex of this parabola is at 2, 1. Since 1/8 is positive, the parabola opens upward. And because 1/8 is between 0 and 1, it's going to be wider than our original y equals x squared. Any equation of the form y equals x squared plus bx plus c can be written in standard form. The standard form of the equation of a parabola with vertex hk and axis of symmetry x equals h is y equals a times x minus h squared plus k. If a is greater than 0, k is a minimum of the related function and the parabola opens upward. If a is less than 0, k is the maximum value of the related function and the parabola opens downward. Write y equals -x squared minus 2x plus 3 in standard form. Identify the vertex, axis of symmetry, and directions the opening of the parabola. Well, the first thing I want to do is factor out that -1. If you want to write the 1, you can. We don't usually. And we're going to have to complete the square. So to complete the square, we take the coefficient of x divided by 2 and square it. So I'm going to get 1, and if I add 1 on the inside, I'm really adding a -1. So to keep it balanced, I'm going to also have to add 1 on the outside. So it's like I added nothing. And we can look back at what we had when we divided by 2 to know what's going to go inside our parenthesis for a completed square. So it's going to be x plus 1 squared plus 4. Since we have it in standard form, it's easy to see our vertex now is going to be at hk, and it's always the opposite sign here because it's x minus h, so our vertex is going to be at negative 1, 4. The axis of symmetry is x equals h, so x equals negative 1, and because a is negative, it's going to open down. And that should all be very familiar from what we did in Chapter 6. Actually, we answered more questions in Chapter 6 than that. And again, this looks like we did in Chapter 6. Graph. Our vertex is going to be at the origin, 0, 0. And they planned on using symmetry. They just got 3 points to the right of that. So we can graph 0, 0, 1, 2, 3, 18 might be a bit of a stretch. It looks like they have 3, but they don't. And then we know that if we go 1 to the right, we go 2 up. We go 1 to the left, we also go 2 up. And we can graph our parabola. 2b is already in standard form as well. So we can see our vertex is going to be at 1, negative 5. And I went ahead and grabbed 2 points to the right of that as well. So 2 is at negative 3. 3 is up to 3. And 4 will be at 13, which is beyond my graph. And then I can use symmetry and get points on the opposite side of it as well. Notice that these two graphs are identical, just our new graph is translated 1 unit to the right and 5 units down from the original. The shape of a parabola and the distance between the focus and directrix depend on the value of a in the equation. The line segment through the focus of a parabola and perpendicular to the axis of symmetry is called the latus rectum. It's perpendicular there. The endpoints of the latus rectum lie on the parabola. In the figure at the right, the latus rectum is segment AB. The length of the latus rectum of the parabola with the equation y equals a x minus h quantity squared plus k is the absolute value of 1 over a units. The endpoints of the latus rectum are 1 over 2a units from the focus. Equations of parabolas with vertical axis of symmetry are in the form y equals a times x minus h quantity squared plus k and are functions. Equations of parabolas with horizontal axis of symmetry are in the form x equals a times y minus k quantity squared plus h and are not functions. Again, this can't be a function because it's going to fail the vertical line test. This chart will be very useful to you. You may want to put it on a note card as well as in your notes for ease of access. I'm not going to read the whole thing. I'll let you guys copy that down. We've done the y equals quite thoroughly, and the x equals is pretty similar. So this is going to be a new experience. We're going to graph x plus y squared equals 4y minus 1. So this time our y is squared is going to open to the right or the left. And when I start to put it in standard form, I can see it's going to open to the left because my a is negative. To complete the square, we need to take the coefficient of y this time, divided by 2 and square it. So we have negative 2 squared is 4. So if I add 4 inside the parenthesis, again, what I'm really adding is a negative 4. So I need to add a positive 4 on the outside to keep it 0. And to see what I have for my completed square, if I look here, when I divided by 2, I had a negative 2. So I'm going to have y minus 2 squared plus 3. I wrote the standard form underneath there so we can see that a is negative 1, k is 2, and h is 3. The vertex is hk, so h was 3 and k was 2. The axis of symmetry is at y equals k, so y equals 2. The focus is at h plus 1 over 4a, so 3 plus 1 over 4 times negative 1, and k is 2. So I get 11 fourths 2, and the directrix is x equals h, so 3 minus 1 over 4a, so 1 over 4 times negative 1, so I get minus negative becomes a plus, so 3 and 1/4, and a is negative, so it's going to open to the left. And it doesn't matter if it's x equals or y equals, the lattice rectum is 1 over, absolute value of 1 over a, so that's going to be 1. Now, in the book, they plan on you just using those facts to draw the graph. So we have our our focus, directrix, axis of symmetry, and we know that it's going to open to the left, so we could sketch a graph. I started to say that your table feature couldn't be useful in graphing this, and then I came up with an idea. I typed in the inverse into the table feature, and so instead of x equals, I typed, well, of course we have y equals in our table feature. Instead of y, I put an x. So then when we scroll through the table, the ordered pair 3, 2 in our graph is going to be 2, 3, -1, 4, -6, 5. And you can scroll through and get as many points as you'd like. And plot them as you will. The 52-meter-long Hummel Arch Bridge in Manchester, England is supported by cable suspended from a parabolic steel arch. The highest point of the arch is 25 meters above the bridge, and the focus of the arch is about 18 meters above the bridge. Let the bridge be the x-axis, let the y-axis pass through the vertex of the arch. Write an equation that models the arch. They told us the vertex is 25 meters above the bridge, so it's at 0, 25. H equals 0, K equals 25. And the focus is at, typo, should be 0, 18, not 12. Use the y-coordinate to find A. So from the chart, we had the focus at H, comma, K plus 1/4 A. We know K is 25, so all I have left to solve for is A. So we can subtract 25 from both sides. So I've got -7 equals 1 over 4a. So if we multiply both sides by 4a, we get it out of the denominator anyway. So if -28a equals 1, we can divide both sides by -28. And we have a equals -1/28. And that's all we needed to finish our equation. So we've got y equals -1/28 times x minus, we said h was 0, so minus 0 isn't very interesting. We'll just leave that out, plus k was 25. And since h was 0, those parentheses were unneeded, we could just write it as y equals -1/28 x squared plus 25. The lattice rectum is helpful in graphing. If we do the absolute value of 1 over -28, we're going to get 28. And half of 28 is 14, so we can see that we need to go through the points -14, 18, and +14, 18. 14 units on either side of our vertex. And according to the length of the bridge, the graph must pass through the points -26, 0 and 26, 0. And if we start with our vertex at 0, 25, and plot those 4 points, we've got a good approximation of the graph. Now, of course, the part that goes underneath the bridge does not exist. In summary, they gave us that same chart we've already looked at, where we have parabolas that can open up or down that we've already seen, and our new friends that are no longer functions that can open right or left that we can also graph.